Good morning, students. Today we are going to learn about collision theory of bimolecular reactions, and from which we can understand the rates of bimolecular reactions and the speed with which the reactant can give a product. The learning objectives in this lecture are we are going to see what is actually the theory behind a chemical reaction. So it is to know about the theories of reaction rates. When we come for the theories of reaction rates of chemical reactions, we are having the first and foremost theory as collision theory. The second objective is to understand the postulates of collision theory, which means the assumptions which are made in a collision theory building up. And the third objective is to learn about the energy barrier diagram, what is here to explain the conversion of reactants into products. And the last objective is to derive the equation for collision theory rate constant of bimolecular reactions. So the postulates of the collision theory we must learn here. For any reaction to occur, the molecules must approach each other. That is the first assumption. The molecules, when they approach each other, they have a chance of hitting with one another, and that hitting is known as collision. So, a reaction occurs on the collision of two molecules only if they come closer to each other, and this collision must associate with molecules of certain minimum energy, what is the energy possessed by the molecules. So that minimum energy is going to change here. So the second assumption is the collision between happen between the molecules other than activated molecules do not lead to chemical reaction at all, which means that collision happening between molecules other than energy rich molecules will not give to product formation, or it will not lead to chemical reaction. If it is simple collision with little energy molecules, means it will not lead to product formation. Only collision occurring between the molecules which are activated molecules having energy high, that will lead to chemical reaction or product formation. The third assumption explains about the activation energy, that is the minimum energy in excess to the normal energy possessed by the colliding molecules, what they must acquire before converting themselves into products by means of successive repeated collisions is known as the activation energy. So here let us recall the definitions what are coming as the postulates of collision theory. You should know two important definitions here. One is threshold energy, another one is activation energy. The minimum energy which the molecules must be associated with each other before they are undergoing mutual collisions that may result in a chemical reaction is termed as threshold energy, and the number of molecules which are possessing this energy equal to threshold energy will be having an opportunity to give the product formation. So even with a small rise in temperature, this threshold energy may be obtained, what is known as the effect of temperature. The rate of reaction increases considerably even with a small increase of temperature. As and when you supply temperature, which is in the form of heat energy, that will be distributed among the molecules of the reacting species, and that will be felt by the individual molecules which are involved in collision, and automatically their energy will increase, and that will lead to a product formation. According to collision theory, there is a certain minimum energy which is known as threshold energy, which the colliding molecules must acquire before they are in a position to react. This minimum energy, what has to be acquired by the molecules, is obtained by successive collisions. Not all collisions are effective in giving products. Only collisions which are accompanied by molecules having certain minimum energy will give you the product. So this is the first idea. Next, most of the molecules definitely have less kinetic energy than the threshold energy, and that threshold energy will be required for collision to result in product formation. So what the molecules will do? So they must possess some excess energy, which having energy less than the threshold energy must acquire in order to give the final product. and that energy is known as activation energy. So here activation energy is a difference in energy between the threshold energy and the energy possessed by the molecules initially. So we can write in an equation activation energy is equal to threshold energy minus energy possessed by the molecules initially. So the molecule is having a original energy what is known as E1, what is represented as energy of the molecule, what it is ready for collision, plus the energy what it is going to gain by its successive collision, what is represented as E2 divided by RT. So which is given as the total thing, what is E power minus EA by RT. For simplicity, this is the condition that a pair of molecules must have the energy necessary for the reaction. So when you have 2 moles of hydrogen iodide giving as a product hydrogen gas and hydrogen gas, here these two hydrogen iodide molecules must collide, and this collision must result by reaching a minimum energy, what is called the threshold energy, whereby you are having the possible chance of the hydrogen iodide dissociating into individual hydrogen and iodine molecule. The reaction for the present purpose is considered to take place in the forward direction. So a forward reaction is one where you have the molecules of the reactant type collide with a minimum energy what is necessary for the proper orientation of the molecules to give the product, and that energy once it is acquired by the molecules reactant type of molecules, they will suddenly decompose into the product of required type. Evidently the two molecules of hydrogen iodide will definitely collide with each other before the bonds existing between hydrogen and iodine can break to form new bonds between two hydrogen atoms and two iodine atoms. So this will give rise to one molecule each of hydrogen and iodine. Let us see what is the energy profile for a chemical reaction according to the rate at which the reaction proceeds. Here we are going to consider what is known as potential energy along the y-axis and the progress of the reaction along the x-axis. So it is a potential energy versus what is known as a progress of the reaction along the x-axis, what you are going to call it as an energy barrier diagram. In this energy barrier diagram, we are going to represent the energy of the reactants and what is the energy of the products and what is the energy the molecules must possess to convert themselves into the product. So three states we are going to represent with the notations X, Y and Z. X is the initial stage, Y is the final stage and Z is the intermediate stage. X is nothing but the original energy possessed by the reactants in the initial state, and Z is the energy which is gained by the reactant molecules by means of successive collisions with each other, by which they are now ready to convert themselves into a product with the proper orientation of structures and bonding between the atoms. And finally the state Y, where you have the products are now ready to separate, which is as AB and C, what is a new type of product. If you see this diagram, the difference in energy of the molecules in the original and the state Z is represented as the energy barrier, what is known as the activation energy required for the forward process of A plus BC converted into AB and C. So once this is obtained means it may happen in two ways. Either it may proceed in the forward direction giving the products of AB plus C type, or the transition state what the activated molecules are having extra energy can give back into the original stage what is A single molecule with the BC molecule as the second type of molecule. So both these things are possible. Now the energy what is required for the forward process is greater, whereas the energy required for the backward process is represented as E2. So here we can see that the energy of the reactants taken initially is lower the energy what is required for the products formation. So here the energy difference between these two reactants and products original energy is known as delta E, and this type of reaction where it is required energy is required in excess than the original reactant molecule is known as an endothermic reaction. If n is the number of molecules of the same kind that are involved in the bimolecular reaction, then dx by dt is given as equal to k into n squared. So this k into n squared is the number of molecules with respect to the collision involved. Then we can rewrite this by comparing with the equation, previous equation number 8. What is z dash into e power minus e by rt is equal to kn square. And then when we bring this rate constant k along this side, you will have the equation taking into a new form z dash divided by n squared into e power minus e1 by rt. Now z is the now twice the number of molecular collisions per cc per second when two molecules take part in every collision. Hence we can write the equation z dash is equal to 4n squared sigma squared into pi rt by m whole power half, where sigma is the molecular collision diameter and m is the molecular weight. Z dash is the total number of molecules colliding per cc per second of the gaseous reaction, which is twice the number of collision number. So Z dash is equal to 2Z. Now Z dash is 4n squared by m sigma squared into pi rt by m whole power half e power minus e1 by rt. Now this n squared when compared with the previous experimental Wright law equation dx by dt is equal to kn squared. N squared will get cancelled and we will have k equated to 4 sigma squared into pi rt by m whole power half e power minus e1 by rt, which is nothing but z into e power minus e1 by rt, where z is equal to 4 sigma square pi rt by m by half, which is known from kinetic theory of gases as the collision number. This z is defined as number of collisions per second when there is only 1 mole of reactant per unit volume. So thus we are going to take this collision number for deriving the rate constant of bimolecular collision theory, rate constant. And now on taking logarithm of equation 10, we can get the equation taking into the form log k equal to log 4 sigma square by rt by m whole power half minus e by rt. The exponential will get removed here. So differentiating this expression with respect to temperature, we get the expression changing into the new form d log k by dt, which is equal to 1 by 2t plus e by rt squared. So when on comparison with the other denominator rt squared, this 2t is small and this can be neglected. Now the collision theory equation reduces to this form d log k by dt is equal to E by RT squared. This equation is now identical with Arrhenius equation, which is after differentiation with respect to temperature, the k equal to A into e power minus EA by RT equation will change into. Here we have the value of collision diameter, collision number calculated from collision theory. It is thus possible to compare it with the experimental value of the frequency factor obtained. If the molecules are of two different types, A plus B reacting to give a product, the collision theory equation will take the form Z is equal to sigma squared 8 pi RT into M1 plus M2 divided by M1 M2 whole power half, where the M1 M2 values are the respective molecular weights of the species A and B taken for the reaction. It was found that in certain reactions where the experimental and calculated values of K differ to a certain extent. In these cases, the values were not the same as proposed by collision theory. Example, we are having the reaction between vapors of ethanol and acetic anhydride. And one more thing that is the example, another thing what I can give here is the combination of two molecules of ethylene. In these cases, if you see, the experimental results does not agree with the collision theory rate equation calculation. So, in order to overcome those disparities, collision theory introduces a correction factor known as probability factor or steric factor, which makes allowances for certain effects which will account for the deviations arise from the ideal behavior. The value of P varies from unity to 10 power minus 8 depending upon the nature of the reaction. Collision theory has three failures to discuss. Firstly, the collision theory introduces a correction factor known as probability factor, which is introduced to alter the equation to suit with the experimental rate results obtained, where the structure and properties of reacting molecules were not found to be matching with the experimental results. This is one failure. So, it is not possible to correlate the value of probability factor introduced in collision theory with the structure and properties of reacting molecules. So, that is one failure. Secondly, it is not possible to give explanation for abnormally high rates proposed by collision theory. The rates observed experimentally were somewhat lower than the rate obtained by collision theory calculation. This is the second failure. And the third one is there is a logical weakness observed when reversible reactions are studied. In the case of reversible reactions, where you have a forward reaction proceeding, giving products, and that product giving back the reactants, we are not able to correlate collision theory equation with the experimental results obtained. So these are all the failures by which collision theory was found to be not successful.